Hello everybody, welcome to lesson 4.4, which explains increasing and decreasing functions and the first derivative test for relative extrema, meaning we are going to learn how to use calculus tools in order to find whether or not a function is increasing or a function is decreasing. Now, in this book, I would say take a moment, read these words. If you feel like you don't understand these words, you should definitely watch the freestyle, okay? And specifically, I'll mention that this phrase right here and this mathematical phrase right here, if you feel like you don't understand what that phrase means or you wouldn't be able to express what that phrase is out loud, then you should definitely watch that freestyle. It's long though, so I'm going to move on. I moved it out of the video. I would like to actually just do these examples, and specifically, I'm looking to do them with the procedure that he's given us. It's just that there's a little piece of this that I feel like isn't really clear, and I want to make sure that I make it clear first. And it's not optional. This is required, so I'm putting it into the video, okay? Please make sure that you have this in your notes. You have found a maximum for your function if you can see that the derivative has a positive value on it, because that's where your function was increasing, and then you can see that your derivative has a negative value on it because then your function was decreasing. All right, and the notation for this is that if f prime of x was positive, then f of x is increasing. And then we're going to look, at a further moment in time down the line on the x-axis or wherever, and we say that if f prime of x was less than 0, meaning that the derivative is negative, then f of x is decreasing. All right, that is when you have found a maximum. And again, I'll refer you to the freestyle if you feel like this notation that I'm using here is not clear. All right, so then you will say that you have found a minimum if f prime of x was decreasing, meaning it was less than 0, and you could say then that you see later on that f prime of x was greater than 0 because my function decreased and then it increased again. And we need this for putting together our final answer down there. So this is something you might want to actually put onto your mega cheat sheet, although we're going to do enough of these for the rest of the year that you should like internalize it. I'm not making a memorizing quiz for it or anything like that. It's just that's what we're doing, and you'll see. And by the way, that was my slope was negative, and right there my slope was positive, and I'm making sure that you could see those. So his procedure says let's list our domain restrictions. And when we list our domain restrictions, we take a look at the function and try to decide are there any values that we can't have. And let me rewrite this function really quickly so that it looks like it is actually a cube root. And the stuff on the inside is squared and the cube root's on the outside. So when I see square root, I get worried about taking a square root of a negative number, but there's no square root here. This is a cube root here. And I'm remembering some things about cube roots. For example, the cube root of, say, 8 is going to be 2, but the cube root of negative 8 would also just be a negative 2. The cube root of negative 1 would just be negative 1. So I'm not worried about plugging any negative numbers in. I'm not worried about plugging in 0, for example. I can just get 0. It's not a rational function. If it was like this, I'd have a problem. I'd be worried about when this bottom amount is equal to 0, but I'm not worried about that right now. When we get to the derivative, it will be in the denominator, and then I'll worry. Okay, so for now, I can say that step 1, we check the domain. No restrictions on domain. at all, because we can take the cube root of anything. So then step 2 says we're going to find critical numbers. And I've already highlighted these just so you could see them. The derivative, I need to set it equal to 0. The derivative, I need to check to see if it's undefined anywhere. And I was mentioning that if I had this bit in the denominator, that would be an important moment. Well, that's what's about to happen. So I have the derivative of x is going to be 2/3 times x squared minus 9. And the derivative goes down by -1/3, right? So it went down by 1. And then don't forget, there's the chain rule. There's that hook-on piece, which is that you need to take the derivative of the inside. And always, always, always want to remember that chain rule piece where it's right here. I'm saying that the derivative of x squared is 2x and the derivative of -9 is 0, okay? Now I want to rewrite this function so it looks just a little bit neater. And I'll say that this 2x and this 2, they're both on top. So there's my 4x. And then on bottom, what do I have? I have a 3, and I have that cube root of x squared minus 9. And, yeah. And it's not squared anymore, right? Because that squared came from being part of the 2/3, which turned into a -1/3. So now I'm good. I've got the derivative. Yay. How do I know when this function is undefined? I think the part where I set it equal to 0 is pretty easy. Let me do it like this. So I'm saying that on top, right here, if I say that that is equal to 0, then it doesn't matter what I get on bottom. I'll be dividing it into 0. So let me do this. 4x equals 0. Divide by 4. Divide by 4. If x is equal to 0, and then I have a situation where if I plug that 0 in right here, I would get 0 over something. And it would just, my answer would then just be 0. Because remember, I'm not dividing by 0. I'm dividing into 0. And if you divide into 0, you just get 0. So that part wasn't so hard. Just set the numerator equal to 0. Set numerator equal to 0 to find when the function is equal to 0. But when is my function undefined? Well, that's when I want to know, when am I dividing by 0? So I'm going to set the denominator equal to 0 to find when it's undefined. So I say 3 times x squared minus 9 being underneath a cube root. Whoops, I forgot to write it down. There it is, the cube root. And then set that equal to 0. I'm going to divide by 3 so that these go away, and 0 divided by 3 is 0. So I have the cube root of x squared minus 9, and you might not feel like you know what to do with that. So let me just pause for a minute. If it was a square root, we would just square it. It's a cube root, so let's just cube it. And both sides. And when I cube 0, I get 0. And then on the inside here, this x squared minus 9 just pops out. Now, if you're wondering what it is I'm doing here, I'll mention, and let me go back up to here. When I took the cube root of -1, I just got -1, right? Well, there's another, and when I took the cube root of -8, I got a -2. It's just, you didn't really, I know you know that 8 is 2 cubed, but what you might not have known was I could write it like that and then take the cube root of it. And so what happens is the -2 just popped out. Well, that's what's happening here. So the stuff that's underneath here, it just pops out, okay? And it comes down right here. So does that happen every time? Yes. So when you're looking into the denominator, you have some sort of root, a square root, a cube root, fourth root, whatever. If you just look at the stuff that's on the inside and bring it out, in this particular case, you'll always be setting it equal to 0 because you're looking to see when it's undefined. So you can just skip all of these steps and go straight to here. That's all that'll be a shortcut for you in the future. All right, so now I'm going to add 9 to both sides. I get x squared equals 9. Take the square root of both sides, and then I get x equals positive or negative 3. Now, that's one way to finish this problem, but I'll note that other students would find it easier to just, say x minus 3 times x plus 3 equals 0. So these are your two methods for solving x squared minus 9. And then you get this one's equal to 0, this one's equal to 0. So you get x equals 3 and x equals negative 3. And either way, you got the same answers here as you would have there. Okay, so now we know what our critical numbers are. So our critical numbers, it's always a good idea to write them down, are going to be x equals 0 and x equals positive or negative 3. And he says, oh, no, he says domain restrictions cannot be critical numbers. We don't have any domain restrictions, so we're not worried about that right now. But let's not forget it for future problems. Locate critical numbers and domain restrictions on an F prime number line. So what is an F prime number line? This is an F prime number line where I'm writing down that 0, I'm writing down that positive 3 and that negative 3, and those are my critical numbers. Now, if you have to write down this part right here. You must state that that is the number line for the derivative. Otherwise, you run into some trouble. You might lose points for justification. You do have to give a justification for your reasoning on what the intervals are on a free response problem. So you don't want to miss out on those points. So make sure you always label it. Okay, now it says locate those critical numbers and domain restrictions on that number line and label them as critical numbers. We've got that written down. So now we're on step 4. So this is step 3. And by the way, all of that was step 2. All of that where I'm finding those critical numbers is right there. So step 4 is going to be for me to test the sign of f prime of x. Now, I'm going to do this like this. At some point, you might be able to avoid making the table here. You might be able to just sort of eyeball stuff. But for the purposes of instruction, I'm going to show it to you each individual step. Now, first of all, I'm writing down right here that I had my critical number negative 3, I had my critical number 0, I have my critical number positive 3, and I'm saying to you that I already know what happens here. My derivative is undefined at 3 and negative 3, and I know that my derivative is equal to 0 at 0. So those parts I'm not looking for. I've already found them. What am I looking for? Well, what I'm looking for is, if this is a critical number, if this is going to be some sort of minimum, which I'm just giving you a hint, it is. If this is supposed to be some sort of minimum, what's happening nearby it is that I should have I should have, and I'm trying to, hold on a second. I should have a negative slope and I should have a positive slope. And then if this right here is some sort of minimum, then this should be a negative slope and this should be a positive slope, because that's how the shape would be turned into some kind of minimum. Now, how did I know that those were going to be minimums? Look, dude, I'm looking at the answer key. So that's how I know. But I will also show you the graph in a moment. But before I do, I wanted to mention then that in order for me to know what the derivative is, I can't check at negative 3. I need to check somewhere nearby to negative 3. So, for example, negative 4 would work. And then I need to check something in between negative 3 and 0, and I'm just going to pick negative 1. Then I need to check something in between 0 and 1, so I'm going to pick a 1. And then out here, I'm going to go a little bit bigger than 3. So let me write this down. I picked that. I picked that, I picked that, and I picked that. You can pick anything you want, okay? You're allowed to pick a number, like say I could have picked negative 10, or I could have picked negative 2 instead of the 4s and the 1s, all right? So those are my options. Now let me show you the graph really quick. Here it is. Boom, there's my minimum right there at -3. There's my minimum right there at +3. And there's a maximum up here. And we're going to get that in just a moment. Okay. So here we go. Let's take a look at it. So I'm in here and I'm saying that I'm just checking the value of the function at these points. I'm not trying so hard to actually find what the number is. What I want to know is, what is its sign? So I'm looking at this function right here, and I'm looking at the numerator and deciding what I get, and I'm looking at the denominator and I'm deciding what I'm going to get. And so I'm just trying to show just the sign. So if I plug in a -4, I have 4 times a negative number, and it doesn't even matter what the negative number is. I know that 4 is positive, and so I'm not even going to write the 4 down. How about we just do this? I'm going to say 4 is positive, and the number that I'm multiplying by is negative. So on top, I'm going to get a negative. Then when I'm looking at the bottom number, 3 is positive, and then I'm looking at the cube root. Ready? The cube root. Oh, this is not big enough. The cube root of x squared minus 9. Now, if I plug in that x squared was a -4, that will turn into a +4, okay? But that +4, when I square it, I'll get, well, a -4 times a -4 turns into a +16. When I look at that 16 and I take away 9, is that number positive or is that number negative? I know I have to take the cube root of it, so if it was negative, I would get a negative out. But let's look at it. 16 minus 9 is positive. So what I have is a negative divided by a positive, which means that my slope is going downwards. It's going downwards at -4. So I'm going to put that on my number line. It is going downwards, just like I said it would. I looked at the graph. I cheated. Okay, so then what happens at -1? Well, 4 was positive and 1 is negative. So I have a positive times a negative on top, and on bottom I have -1 being squared minus 9, and I'm supposed to take the cube root of that. Well, the -1, when I square it, I get a +1, so that's going to be +1 minus 9. And when I take the cube root of that, I'm going to end up with a negative number. So on top, I had a negative times a positive. That's a negative. But on bottom now, I also will have a negative, which means a negative divided by a negative is a positive. And hallelujah, I end up with a positive here, just as I predicted. And then let's check this one. So 4 was negative, 1 is positive. So on top, I have a positive. But on bottom, what do I have? I have that 1 being squared minus a 9, and I'm taking the cube root of that. Well, again, that's a negative number. So I'm going to say I have a positive divided by a negative, which makes this be a negative. So let me check to see what happens when I plug in 4, and I get a positive times another positive, which means on top I have a positive, and on bottom I have the cube root of 3 with the 4 being squared minus the 9. That's going to be 16 minus 9. That is also a positive number, and so I end up with a positive. And so I've just determined that this 3 and this -3, those are minimums. And then, hey, take a look. How am I deciding that they're minimums? It's this blue business right here. So if it's going down, oops, this pen is what I meant. If it's going down, this is going down, then and then it's going up, and this is going up, then I have a minimum. And the same thing over here. It's funny because now if I want to know where there's a maximum, I say, well, if it's going up, well, this is going up. And then if I want to say, oh, well, this side is going down, well, this side is going down. So that makes 0 be our maximum. And so I want to write some answers down now. We've been on this problem for a while. Here we go. So my relative minimums are at x equals 3 and -3, and my relative maximums is going to be at x equals 0. Now, he actually gives these as points, and so I'll say if you need to go in and evaluate the original function, here is the original function. What are you doing? You're doing f of 3. You're going to get 3 squared minus 9, and then you're taking the 2/3 root of that. But it turns out 3 squared is 9, and 9 minus 9 is 0, and so 0 to the 2/3 power is just 0. Same thing if you did the negative version of that. Because you square it, take that -3 and you square it, you end up with the same answer, okay, because the negative disappears, and so you end up getting 0. This last bit here, if you plug in actual 0, then that's kind of fascinating. You get 0 squared minus 9, and you're taking the 2/3 power of it, so you just write down the answer is -9 to the 2/3 power. And if you want to be precise, don't put any parentheses down. But if you accidentally put parentheses down, you need to make sure you put those parentheses around the whole amount, -9. So it's better to not put any parentheses down at all. But anyway, so that means the point is going to be positive and -3, 0. That's the height you're at. And the point here is going to be 0 and -9 to the 2/3 power if you put parentheses down. Otherwise, I like it the way it looks. Well, yeah, maybe you do want to put the parentheses down. It's kind of compulsive, isn't it? Okay, so what intervals was it increasing or decreasing on? Your intervals are actually written for you already. You just didn't realize it. Your intervals then are going to be from infinity to -3, and then from 0 to 3. And all you have to do is just throw them down. So where you see the negatives, you say the function is decreasing from -infinity up to -3, and you can do those closed brackets, no problem there. Here you're supposed to do an open bracket, but they don't take points off if you mess that up. And then from 0 to 3, and again you can use those closed brackets, it's no problem at all. And then we say the function is increasing everywhere that you saw right here, the positive slopes. And so I'm saying that it's increasing from -3 up to 0, and from 3 up to infinity. So here we start with number 2, and we're going to follow the procedure here. So number 1, I'll note that the domain is unrestricted. How do I know? Well, I could plug in anything I want for x, and sine is also defined everywhere, so I could plug in anything for sine of x, and I'm not going to have any trouble being able to find the answer. There's not rational function here. I'm not worried about taking the square root of a negative number, so domain is unrestricted. I could be anywhere. Now I am noting this right here, and I'll talk about it more in a minute. So step number 2 is to find those critical numbers. So y prime will end up being 1 minus 2 times sine of x. 2, well, what's the derivative of sine? It's cosine. All right, now take a moment and actually write that thing is equal to 0. Don't just be lazy and put that equal 0 on the other side. I know I do it, and I've seen you guys do it, but take a moment and actually set it equal to 0. There's a point awarded for stating what the derivative is, and you want it to be very clear for the grader that you have found the derivative somewhere. Then there's probably a point awarded for setting it equal to 0, although usually you do actually have to find the answer. So I'm going to take these 2 cosine of x and I'm going to add it to both sides, but I'm not showing all my work on this. I don't have to. 1 equals 2 times cosine of x, right? Because I added that to both sides. I'm going to divide by 2. I'm going to divide by 2. And what I'm telling you is that I need to know when cosine of x is equal to 1/2. Well, I have the unit circle memorized. Let me take a look. This is going to be my 30 degrees, and so and this is the guy that I like to use right away. The square root of 3 over 2 is the length of the x-axis piece, and the height is going to be a 1/2. Well, that was 30 degrees, so that wasn't good because I got that square root of 3 over 2. What I wanted was the 60 degrees, where I remember that those two values are swapped. So this is 1/2 and the square root of 3 over 2. And so what is 60 degrees? That is going to be pi over 3. So I can say that I have just found that x is a problem, meaning I get 0 when it's pi over 3. And then on the other side, I will get it at 5 pi over 3 as well, okay? That's on over here, which is the same thing as having a pi and taking away a pi over 3. So that's why I only have 5 pi's over 3 instead of 6 pi's over 3. So now that I have my critical numbers and I am labeling them, right? Labeling them, I'm actually going to do my number line, which again, I will label. This is my y prime number line, and I have my pi over 3 and I have my 5 pi over 3. And I'm checking to see what's happening to the values in between those numbers, because I already know that at pi over 3, I get 0. And then at 5 pi over 3, I also get 0. So I want to know what's happening in between those. And so I've got my number line, and here I go. What are some values I could pick? Well, I see that the domain is restricted here, but that doesn't mean that I can't find the derivative's value there. Does that make sense? I am allowed to find the derivative's value there because the domain was unrestricted. So, within this interval, there weren't any problems, but even outside of this interval, there weren't any problems. So I can tell you that I know that it's okay to use 0 here, and I know it's okay to use 2 pi here. And then right here, I'm going to use pi. It just makes my life easier because I'm evaluating that function. I have 1 minus 2 times cosine of something. Well, I want to do cosine of 0 because that's just 1. That's easy to do. So this is 1 minus 2 times 1 is going to end up being 1 minus 2, ends up being a negative number. Okay, I know it's technically -1, but I wasn't even caring what that number was. All right, so then I have 1 minus 2 times cosine of pi, and cosine of pi, let me think about it. Cosine of pi is over here. This is pi in radians, and so cosine would be -1 and sine would be 0. So I'm going to say I have 1 minus 2 times cosine would be -1, and so that's a 1 plus a 4. That's going to be a positive number. And then down here at 2 pi, well, what was cosine? Cosine would be 1 and 0. So right here I have 1 minus 2 times cosine of 2 pi is going to be a positive 1. And then I get 1 minus 2, which ends up being a negative number. And so there's my positive, there's my negative. And I like to just kind of draw it to remind myself. I just finished, by the way, step 4. I want to find my increasing, decreasing. I want to find my mins and maxes by actually sketching it. So I'm going down, I'm going up, I'm going down. So this is going to be a min, and this is going to be a max. Now, take a moment and check it on your calculator first. You're not testing right now, so let's take a look at that graph. And we're looking at it, and here it is. And by the way, I did a neat little trick here where I'm just, putting in some values of pi so that I can see those values of pi on the graph. So here, there is 0. That right there, that right there is pi over 3. Notice that it was decreasing from here to here, and then it's increasing all the way up to there. And that moment in time was 5 pi over 3. And then from here, it goes down, 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 and it stops decreasing at 7 pi over 3. But that's past my interval. I don't care about it. At 2 pi is where I was supposed to stop. So that's why I'm saying that I'm stopping there. And I didn't mention having another critical point over here because I didn't get to that part of the graph because I had it restricted. All right, so now we could just write these values down. So I say it's increasing. Oh, and by the way, for those of you that struggle with a notation on interval notation, again, that's infinity to pi over 3. And that's 5 pi over 3 up to positive infinity. And so I'll say that the function is decreasing from negative infinity all the way up to pi over 3. And that I start up again at 5 pi over 3, and I go up to positive infinity. And then it is increasing on that big long piece from 0 up to pi over 3. Now note one thing right here, which is this guy. That's the domain restriction. Very important, that domain restriction, because you might get the wrong, you might not get the point if you put a bracket there, because the domain was specifically restricted. I'm not sure, I haven't been a grader, so I don't know. And then when we list those maximums, you just plug in what you're getting. You can't, by the way, I noticed on the test a couple of you had tried to like leave something like cosine of pi over 3 in your answer. You can't do that. You do need to actually evaluate it. So if we evaluate them, which in the interest of time I will leave to you to do, what we get is this. And our min, we will do this.